In this section of Chapter 3, I'd like to discuss additional problems on limiting reagent. The limiting reactant is the reactant that present in the smallest stoichiometric amount. In other words, this is the reactant that is used up in the reaction. So if you look at the figure, you can see that there are 10 hydrogen and 7 oxygen are mixed together. When you get the products, you get 10 water and there'd be 2 oxygen left over, but there's no hydrogen molecule left. So that means all hydrogen molecules are used up. If I want to write down the chemical reaction, it's going to look like this: hydrogen plus oxygen giving H2O. So if I balance it, this is how it's going to look like. Since they added 10 mole of hydrogen, 10 hydrogen, stoichiometric ratio tells us that for every 2 mole of hydrogen, 1 mole of oxygen is going to react. So for every 10 mole of hydrogen, 5 mole of oxygen is going to react. And remember, they added 7 mole of oxygen. So there'll be 2 moles left over. So that checks out. Now we also learned here that the oxygen was the excess reagent. And that's the typical type of chemical reaction where one of the reactants will be completely used up in the reaction, and the one that is completely used up is going to determine how much product one can get. I mentioned about theoretical and percent yield as I was going over one problem by applying dimensional analysis. Theoretical yield is calculated value, and percent yield would be given by experimental yield by theoretical yield times 100. Now here I need to point out to you that in theoretical yield calculation, our assumptions are reactions are 100% over. So let me write down here, reactions 100% done. And secondly, reactants are 100% pure. And we know that none of these are actually true. Reactions can go up to close to 100%, but it would not go to 100%. We discussed that on the basis of equilibrium in Chem 112. Second assumption is reactants are 100% pure. So on the basis of that, we do the calculation. So always experimental value or actual value is less than theoretical value. It can be close to theoretical value, would never be equal to theoretical value. So usually less than, the percent yield is usually less than 100%. Let's now go over a problem. As I said that we are going to discuss limiting reagent problems. So I would like to go over number 62. And this is on page 111. Question number 62 gives the following reaction. So let me first write down the reaction. 4KO2 plus 2CO2, that gives 2K2CO3, K2CO3 plus 3O2. Let me double check this. 4KO2 plus 2CO2 giving 2K2CO3 plus 3O2. In part A, the question is how many moles of oxygen? So let's write down what they're asking for. Moles oxygen. So how many moles of oxygen are produced when 0.400 mole of KO2 reacts? So 0.400, so this 0.400 mole KO2. So they're basically saying that 0.400 mole of KO2 reacts and how many moles of oxygen are produced. So let's do that, times mole of KO2 at the bottom and I can directly get oxygen. So let's write down mole of oxygen because there's the direct relationship I can see from the chemical reaction. Let's look at these numbers. 4, 2, 2, 3. That means when 4 moles of KO2 reacts, it's going to consume 2 moles of CO2, and that's going to form 2 moles of K2CO3 and 3 moles of O2. So now I'm going to use this relationship in order to get oxygen, how much oxygen is produced in this reaction, because that's what they're asking for. So what values I'm going to use? At the bottom, mole of KO2 would be 4. So 4 moles of KO2, that's going to form 3 moles of oxygen. I highlighted those. And that's going to be the answer. So make sure you get these values and get the answer. In part B, let's draw a line here. Okay, now in part B, they're saying that how many grams of KO2? The question is gram of KO2. How many grams of KO2 needed to form 7.50 gram of oxygen? So we always begin with what is given, which is 7.50 gram of oxygen. So basically from gram of oxygen, I need to get to gram of KO2. But if you look at the chemical reaction is going to show you the relationship between moles and moles. So top numbers that I've shown, 4, 2, 2, 3, these are nothing but moles. So let me draw an arrowhead. So those are all moles. So basically, in order to use any of the relationship between reactants and products, I'll have to change gram to mole. So 7.50 gram of O2, I need to change it to mole of O2. So you know how to change from gram of O2 to mole O2. So 1 mole O2, again looking at periodic table, each oxygen is around 16 and 2 oxygen in O2, that's be 32.0. So 32.0 gram of oxygen makes a mole of oxygen. The question is asking for KO2. So let's go to KO2 now. From mole of O2, get mole of KO2. Again, this relationship I can find by looking at the balanced reaction. Mole of KO2. So there are 4 moles of KO2. So there are 4 moles of KO2 and 3 moles of oxygen. Let me show you how you can cancel the units. Gram oxygen, cancel out. Mole of oxygen, cancel out. This would give you mole of KO2. Once you get mole of KO2, then you need to do one additional step. So I'm hoping that you know. Let me just show you that step. Mole KO2 and gram of KO2. Again, mole gram relation. We can look at periodic table and get this value here. You need to look at the mass of potassium and oxygen mass has to be multiplied by 2 because it's two of them in this compound. So this is how you can do part B of number 62. Now we're going to do number 62C. Let's first write down the chemical reaction for KO2 plus 2CO2 giving 2K2CO3 plus 3 oxygen. Let me double check. Make sure this is a balanced reaction. Before you do any such calculation, limiting reagent problems, mole calculation based on a chemical reaction, make sure it's a balanced reaction. For KO2, 2CO2, 2K2CO3 plus 3CO2. Okay, so it's a balanced reaction. I just checked this. Now the question is in part C of 862. The question is asking how many grams of carbon dioxide. So how many gram carbon dioxide are used when 7.50 gram of oxygen. So 7.50 gram of oxygen, right down here. So 7.50 gram of oxygen are produced. So basically you need to calculate from gram of oxygen to gram of carbon dioxide. So you'll have to use this information, some information from the chemical reaction, because oxygen and carbon dioxide are related by this chemical reaction, and these numbers are 4, 2, 2, 3, and these are all moles, so keep that in mind. These are moles. So before I use those relationship connecting moles of oxygen to moles of CO2, I'll have to change gram of oxygen to moles of oxygen. So my first step is going to be gram of oxygen, the bottom, mole of oxygen on the top. Again, mole-gram relationship, look at periodic table, get the mass of each oxygen multiplied by 2 because there are 2 oxygen. And so that means you have 32.0 gram. 32.0 gram. Again, I rounded off. That's fairly close to 16 for each oxygen. Okay, and next step, if I stop here, I'm going to get mole of oxygen, but I need to go to carbon dioxide. So let's do the step now, connecting oxygen, moles of oxygen to moles of carbon dioxide. So moles oxygen, the bottom, moles carbon dioxide on the top. Okay, now the relationship is 3 moles of oxygen. On the top you'd have 2 moles of carbon dioxide. If I stop here, let me show you that what you're going to get if you stop here. Gram oxygen would cancel out. Mole oxygen would cancel out. If you stop here, you get mole of carbon dioxide. But the question is asking for gram of carbon dioxide. So that means I need to go one additional step. And let me show you that step here. Times mole of carbon dioxide on the bottom and gram of carbon dioxide on the top. We all know mole-gram relationship we get from periodic table. So you look at the masses of carbon and mass of oxygen, make sure you add mass of one carbon plus masses of two oxygen. So each carbon is 12, two oxygen would be 32. So altogether you're going to have 44 gram of carbon dioxide. So let's write down 44.0. I don't have enough space here. 44.0 gram of carbon dioxide. Now this gives you 6.875. If I want to round up to three significant figures, it's going to be around 6.88, and the unit is gram of carbon dioxide. So this is my answer. So it'll be 6.88 gram of carbon dioxide that's going to react.